Hi guys. Okay, so in this chapter 7, bonding, we are going to now finish up with two important pieces. One is the calculations that relate to the calculations that relate to the lattice energy, that is the ionic compounds, and then the calculations that relate to the covalent compounds, and that is the bond energy calculations. But before we delve into these calculations, let us try to understand the theory. So I'm going to quickly walk you through like the concepts that relate to bonds, the types of bonds, predicting the formula of the ionic compounds, the size of the ions, and then we're going to look at the polar, co-charge distribution in the covalent compounds and the partial ionic character. Okay, so all this is going to cover up the theory so you can understand the need for the calculations, or, why are we making the calculations, or why certain numbers appear in a certain way. So anyway, so let's look at, first of all, what is a bond. Bond is actually like it forms when two atoms are chemically combined together. So it is a very definite ratio in which these atoms combine, and that is a permanent change. And unless you apply some kind of, heat or light, or you change some kind of, conditions, then yes, that bond can be broken. But pretty much it is just a, permanent change in which the two atoms are permanently combined with each other. Now, the second thing is a bond is also the arrangement of atoms. So it's not all the time chemical combination. It is just how the atoms are placed, So in the case of metals, they're like kernels, and the name of that arrangement is like kernel. And then in the kernels are like KERNELS. So KERNELS. So these atoms are arranged as kernels, and so that forms the metallic bond. And besides that, how did the idea of these bonds come to us? The idea of the bond came to us, or the concept or the thought of that something exists as a bond between the atoms came to us when we saw the differences in certain substances. For example, carbon. Carbon is made up of 6 electrons, 6 protons, and yeah, it's naturally occurring carbon. But when it is present in the form of a graphite, it is very soft. It's very slippery. It's made up of these pencils, and when you write, it's basically those layers of carbon atoms arranged in a certain fashion. They get slipped. Okay, so it's one form of carbon. Another form of carbon is the diamond. Now, what is diamond? Diamond is the hardest substance known. Here, the arrangement of the atoms is very rigid. Okay, so that's when we see that here the atoms are not even chemically combined to each other. They're just arranged in some pattern. And so the two different patterns in which they are arranged give different properties to that particular substance. In this case, it's carbon. Now let's look at group 4A element. Now group 4A elements are silicon and carbon. Okay, now when silicon combines with oxygen, it gives you silicon dioxide. When carbon combines with oxygen, it gives you carbon dioxide. Silicon combining with oxygen gives you that silica, which is called sand. Carbon dioxide is gas. So one is a solid and the other is an invisible gas, in fact. So you see, and both of them are group 1A elements. So why is that so? Why is silica combining with oxygen giving a solid, which you can see, and it's quite abundant on this earth, versus carbon dioxide, which you can't even see, right? So what is it? So it is all bonding. It all relates to the bonds. So silica combination with oxygen is a different type of bond. Carbon combination with oxygen is a totally different type of bond. Okay, so bond is a force that holds a group of atoms together that gives them the properties. So for example, the properties of the different substances: silica, sand, you can see, solid. Carbon dioxide exists, but you can't see. Okay, now solid, liquid, gases, all these substances that are present, on this earth, the 3 states of matter, it all depends on the arrangement of the atoms and the molecules. So how a substance looks, how it feels, how it smells or tastes or sounds, all those physical properties are again due to bonding. Hardness and the softness, for example, diamond and graphite that we talked about, again, is due to internal bonding. And it's not all the time inside the molecules, but it's outside also, and so, but in this chapter, obviously, we're looking at only the internal bonding. Then the melting point, the boiling point, the freezing point, the conductivity, electrical and heat, malleability, ductility, density, solubility, whether it's an aqueous solubility, means soluble in water, or soluble in a non-aqueous substance. So that all that is properties of these molecules, of these atoms, properties of these substances. And these substances are made up of, all substances are made up of atoms and molecules, and it does define the physical and the chemical changes, right? Now, there are 2 types of bonds, ionic bonds and the covalent bonds. Now, what are the ionic bonds? Ionic bonds, now this thing here, are made up of metals and the non-metals, or metals and the polyatomic ions. So metals give away the electrons, always will form cations, will have a positive charge. Non-metals are going to accept the electrons and they form anions with a negative charge. How many electrons are being lost and gained? This depends on the need to make the bond based on the octet rule. Octet rule means that they want to have 8 electrons in the last shell, and they want to have the 8 electrons in the last shell, and they want to have like a nearest noble gas configuration. So some of them are going to defy the octet also. Okay, so anyways, in general trend is that all group 1A elements are going to form +1 charge, when they will only make 1 bond. Group 2A elements will form +2 charge and will make 2 bonds. Group 3A elements will make 3 charges and will have +3 charge and will make 3 bonds. Group 4A can make, will make 4 bonds, but will have +4 charge, -4 charge, but they also form the bonds by sharing. And this sharing, again, four bonds will be formed. 5A, the charge is -3, and they will make 3 bonds. All the elements that are in group 6A, -2 charge, will make 2 bonds. 7A, -1 charge, will make 1 bond. Group 8A, no charge, no bonds. Okay, so these are just the general trends. But of course, we also have the exceptions. Okay, now exceptions are the elements that have a variable charges, positive charges, such as lead, tin, copper, iron, nickel. So I would say, look at the table in the handout, okay, to look at the other details. But just to give you an idea that based on these charges, they are going to make that many number of bonds. For example, nickel can make 2 bonds and nickel can make 3 bonds. Iron can make 2 bonds and iron can make 3 bonds, and so forth. Okay, now in general, these are the exceptions to, these guys, 5, 6, 7 especially, and 8 also. These guys show some exceptions. And so we see that when it comes to the octet rule is 8 electron rules, means 8 electrons in the last shell. Okay, last shell. And they also have they want to have a noble gas, electronic configuration. So this is the reason why they lose or gain electrons, but they can also defy that octet, and this is because of the presence of d orbitals. D orbitals allow them to expand. So which ones are defying the octet? So hydrogen obviously does not have anything to do with the d orbitals. It only needs 1 more electron. So it doesn't need 8 electrons, so it's a small atom. Similarly, boron, a very small atom, because if in order to have 8 electrons, you need to have that much of capacity also in the nucleus. Okay, next is, look at this, phosphorus. Now phosphorus can make 3 bonds, but phosphorus can make 5 bonds. Some sulfur can make 2 bonds, but sulfur can make 4 and 6 bonds. And we have fluorine, chlorine, bromine, iodine, all of them will make 1 bonds, but chlorine, bromine, and iodine can also make 3, 5, and 7 bonds. Okay. Similarly, lithium, helium, neon, argon, krypton, xenon, all of them will make no bonds, 0 bonds, but xenon can also make 2, 4, and 6 bonds. And again, in chemistry, you can create situations. So these molecules are going to defy the octet. So that is a driving principle for making the bonds. So look at this sodium. Sodium has 11 electrons. It loses that 1 electron. It acquires a positive charge and it becomes neon 10. Then in this situation, sodium is following the octet rule. It is getting fully filled. Once it gets rid of that 1 electron, it is left with full filled orbitals, which are more stable. So we already covered that in the previous chapter. The full filled orbitals are more stable. Okay, so that is the reason why it gets rid of that. It has this is a noble gas configuration. That's what it wants. It's happy with that. Now look at chlorine. Chlorine has 17 electrons. It gets rid of, it adds 1 more electron, so it becomes a chloride. So it had 17, 1 more, 18. So now keep a few things in mind that sodium, when it loses that 1 electron, it becomes sodium plus 1 charge. So the size decreases. The size of a cation is smaller than the size of a neutral atom. But chlorine, when it acquires that 1 negative charge, because remember, negative charge, even though it's an electron that's coming, and yeah, chlorine is happy, it's beginning to look like argon, it's a noble gas configuration, fully filled orbitals, and 8 electrons in the last shell, all those things are great. But that 1 electron that comes, it experiences repulsion from the neighboring electrons. So what happens? It is when it experiences that repulsion, what happens? The electron cloud expands. So the size of the chloride ion is going to be bigger than that of the neutral chlorine atom. Okay, so now keep this in mind that in the solid form, sodium chloride in its solid form, as we see it, is actually existing as a crystal lattice. Now, what is a crystal lattice? Every sodium is surrounded by a certain number of chloride ions, and every chloride ion is surrounded by a certain number of sodium ions. So remember that chloride ions are comparatively very big. So they are going to occupy like their own space. So the size of the ions also makes a difference as to, what it's going to look like. It's lattice structure. So this lattice energy or the lattice structure or a crystal lattice, it's crystal. It is, it's very specific. No 2 ionic compounds can have the same crystal. It all depends on the size and the nature of the anions and the cations. Okay, so now let's look at this has been measured, and that's called a Coulomb's law, where the energy of the interactions between the pair of ions has been measured. And what is that measurement? That measurement is that energy of the 2 ions is measured. E is equal to 2.31 into 10 to the power negative 19 joules times nanometers times Q1, Q2 over R. So what is E? Is obviously the energy in the joules that is present in between the ions, right? Next is R. R is the distance between the ion centers. So this is a value of R. R is 2.76 for sodium. So middle of sodium and the middle of chloride, you combine, so that distance is 2.76. Okay, so that is the internuclear distance, but that is 2.76 angstrom. So when angstrom is converted to the nanometer, it comes out to be 0.276. Now, E is equal to 2.31 10 to the power negative 19 joules times plus 1 charge from sodium and negative 1 charge from chlorine. Okay, so keep that in mind that this plus 1 charge is coming from sodium and minus 1 charge is coming from chlorine. If it is magnesium, Magnesium would be Mg plus 2. So you would put plus 2 here. If it's oxygen, oxygen would be minus 2. So you're going to put minus 2 over here. Okay, where you put the chlorine. And then now what is 0.276? That is the internuclear distance from the center, so that distance is 0.276 nanometers. So after measuring all that, we find that the energy is negative 8.37 10 to the power 19 joules, which means that the more the negative the sign is, the more attractive forces there are, which means that the sodium and the chloride ions are very strongly attracted to each other. Okay, now we also talked about predicting the formula of the ionic compounds. So yes, when calcium and oxygen combine, the empirical formula is the simplest whole number ratio. So it's 1 to 1, 1 atom of calcium and 1 atom of chlorine. But how do they combine? So look at that. Calcium 20, okay, calcium 20, inner core is argon, the outer core is 4s2. Now how do I know it's 4s2? Because it is in period 4, it is in group 2a, it is on the s block, and it is in the second column. Next is oxygen, same way, oxygen is 8, 1s2, 2s2, 2p, 4. So you see, when you put this oxygen close to calcium, you can clearly see that calcium is ready to give away to those 2 electrons from 4s2, so that it begins to look like argon then. Okay, so it looks like argon, as you can see here. After losing. Oxygen, on the other hand, has 8 electrons, and there are 2 unpaired electrons. When these 2 unpaired electrons get paired from the calcium, each of them, so all of them get filled up, and it acquires 2 negative charge, and so it becomes oxide. So now the electronic configuration is that of the nearest noble gas. So this is how this becomes very the nearest noble gas, and then the octet also. Okay, now we already know another thing, that calcium is in group 2a, oxygen is in group 6a, plus 2 and plus 2 minus 2 cancel out, and we just get the formula CaO. Okay, so the CaO is the actual calcium oxide. So it's technically it's 1 to 1 ratio because of this ions, how the electrons, how they can be moved and placed. Now look at aluminum and oxygen. Now the problem here is aluminum can give away 3 electrons, but oxygen only needs 2. So in that case, only in that case, now you're looking to put the negative 2. Now in aluminum, now you put, if 2 atoms of aluminum combine, so that's going to make 6 electrons. So aluminum has to give 6 electrons, so that 3 atoms of oxygen, when they combine, they give 3 atoms of oxygen, and all the remaining 6 electrons have been accounted for. So we have the formula now, Al2O3. Okay, so these are the basics. Now another thing is the size of the ions. Size of the ions is what, as we talked about, that the neutral sodium is bigger than the sodium with plus 1 charge. On the other hand, chlorine with negative 1 charge is bigger than the chloride ion. So you see that? So sodium ion smaller, chloride ion bigger. So that's one thing. Now why though? We see a trend in the periodic table. First of all, when you move from left to the right, okay, or when you move from top to bottom. So top to bottom in the same column, the size increases. Okay, so even, because in general, you are increasing the energy levels. Okay, so the effect of the nucleus begins to decrease. So the effect of the nucleus is also coming down. Okay, now in the same period, if you go from left to right, you will see that the atomic radius comes down. Why? Because the nuclear pull has increased. Because as you go from left to right, you will see that the number of protons are increasing. And as the number of protons increase, and the energy level is the same, okay, number of protons increase, and let me just put this here, the same energy level. Okay, in the same energy level, when that's happening, the nuclear pull is going to increase. So the atom becomes squished, atom becomes like shrink, the electron cloud shrinks basically. All right, so just keep this thing in mind that the size of the ions increases when the nuclear pull decreases, or the nuclear pull increases, the size of the ions decreases. So here is a very interesting example. You have selenium with -2, bromine -1, rubidium -1, so +1, and strontium +2. So which one is bigger? So if you look at it, selenium has 34 protons, bromine has 35, rubidium is 37, and strontium 38. So when there are more protons, more the number of protons, that means the atomic radius has increased. So when the atomic radius increase, the size, the size becomes smaller as the nuclear pull increases. Okay, and on the other hand, here we have the selenium. Selenium is less number of protons, so that means lesser nuclear pull. That means more spread out the electron cloud is. So it just looks like by default a larger size. Okay, now we have the isoelectronic effect. Isoelectronic effect is basically same number of electrons. And now look at this carbon. Carbon originally has 6 electrons. It acquires 4 more. That is why it got -4. And the size is 0.260 nanomolar. On the other hand, you have aluminum, 13 electrons already. It lost the 3 more electron. All of them here, if you look at it, whatever they are doing, all of them will acquire 10 electrons. And the 10 electrons look like the nearest noble gas, neon. But aluminum, when it loses those 3 electrons, then its size is 0.050. Okay, so next is, look at this magnesium. Magnesium has 12 electrons. Magnesium has 20 protons and 12 electrons, and it loses those 2. It looks like neon. Sodium, we already talked about. Losing that 1 electron is going to make them with a positive charge, and the size is 0.095 nanometers. Then you have fluorine, and you have oxygen, and you have the nitrogen. So when these, so as you see here, that the size is continuously increasing, the size is increasing as you go from aluminum to carbon. Okay, and that is, and all of them isoelectronic is, they all have the same number of increasing size. And by size, we mean the radial. Now, what happened? In largest is of carbon, although the number of protons is small, the largest is of carbon. Why? Because there is electron repulsion, and the electron cloud actually expands. Okay, so less nuclear pull basically. But aluminum, the electron cloud shrinks because there is a loss of 3 electrons. Okay, and there is the nuclear pull is increased, is strong nuclear pull. So here this is less nuclear pull, and here you have more nuclear pull. Okay. All right. Now we are going to look at, now you have some idea of the ions, their charges, and the nuclear pull and all that. Now the rest is the lattice energy calculations, which is fairly easy. All you need to do is just add or subtract. That's it. Now the kind of questions that can be asked is like, what kind of energy is it? Is this the energy which is like sublimation? Is it the first ionization energy? Is it lattice energy? What it is? So here is this calculations of the energy terms that are associated with the formation of an ionic compound, which is lithium, here is this lithium fluoride, which is a solid. So you take lithium as a solid, you mix it with fluorine, and you get lithium fluoride. Okay, now the question is, find the value of delta H, or the energy associated with the formation of lithium fluoride. So what are those? So balancing is by the Hess law. So the first step is always the sublimation. Sublimation is when solid gets converted to liquid, a solid gets converted to gas. So lithium first gets heated up, then it converts from solid to a gaseous lithium, and the amount of heat is 161 kilojoules. Next is this lithium in the gaseous state then loses that one electron. When it loses one electron, that is the first ionization energy. And the amount of energy, remember, it's positive. That means it is still absorbing. It is, you have to give the heat. So when it's positive, you're giving heat. When it's negative, it is releasing heat. So in this case, you are also giving 520 kilojoules of heat. Next is fluorine. Now F2, now pay attention here. If you are given, a final molecule with just one halogen, then yeah, you need to do half of the halogen. But if the substance itself is like halogens, then you don't do half. Okay, so here, because it's just lithium fluoride, so therefore this is a bond dissociation energy. So in this case, the F2 bond, this F2 bond is broken, needs to be broken. Okay, so that is the bond dissociation energy. So you balance it by putting half. And so fluorine, this bond energy is 154, but we are not interested in that. We only need one fluorine, so it is half of that. Next is the same fluorine now is going to acquire that one electron. And when that does, it is actually gaining a negative charge. And this is called the energy term. This energy term is called the electron affinity. Okay, so this is called a bond. Let me write this down. Bond dissociation energy. Bond dissociation energy. Okay, so we see now bond dissociation energy is, okay, this. Next is the, which one was that? After that, when fluorine has acquired a negative charge, then it mixes with lithium plus charge in the gaseous state and the fluoride minus charge in the gaseous state, it forms lithium fluoride. So basically this is the lattice energy, which maintains that, every lithium is surrounded by 6 fluorines and every fluorine is surrounded by 6 lithiums. So lithium plus 1 charge surrounded by fluorine negative, and fluorine negative is also surrounded by lithium. Oh, sorry, that's not sodium, that's lithium. Okay, after that you are going to, and generally, as far as I know, it's the 6 atoms. 6 atoms of lithium and 6 atoms of fluorine. Okay, next is you're going to add all these energy terms. And so we have here, okay, so when you add, you are going to bring in the first one, the energy of sublimation, 161 plus 520 plus 77. This is important, plus 77, because you have to half it. Okay, half. So plus 77, then comes plus minus 328, and then comes plus minus 1047. So when you do this math, you see that you have 161 plus 520 plus 77 minus 328 and minus 1047, and that gives you a negative 617. Negative 617 means that this is an exothermic reactions, and all exothermic reactions release heat, and the value of delta H is negative. Okay, so that was the lattice energy term. So like I said, the kind of questions that can be asked is you need to either, find the total energy of the formation of one of the binary ionic compounds, or you will be asked to label that process, like what is it called? Is it electron affinity? It is bond dissociation, it is lattice energy, it is the energy of sublimation, what is it? So that's what it is. Okay, next is the covalent compounds. How are these covalent compounds formed? So we covered this already, that two hydrogen atoms, if they are very far away with a very high energy state, or two hydrogen atoms very far away but at a very low energy state, so both of them will not interact with each other, so they cannot form the bond. There's also a likelihood that hydrogen and hydrogen may give away some of their energy and it come too close. So in that case, again, the bond is not formed. The bond is only formed when the two atoms, they give away so much, all the energy that they have, that they reach a lowest energy place, the lowest energy state, where they are the minimum energy state, that in which the nucleus of one hydrogen talks to the electrons of the other, and the nucleus of the other hydrogen talks to the electrons of the other one. So this way, when the nucleus of one and the electron of the other are attracted, then the bond is formed. Okay, so in this case, this hydrogen and this hydrogen, when they come close together, that optimal distance, the optimal distance between the two atoms that maintains that attraction between the positive nucleus and a negative electron of each other, that optimal distance is called a bond length. Okay, now bond length is favorable when there is a lowest energy state. That's what it is, the lowest energy state, as you can see, where hydrogen is below zero. The more negative the number is, the more stable it is going to be. So the bond energy, where does it go? All the energy that hydrogens had to give away, see, they're at a very high energy state. Where did all that excess energy go? Even though some of it may have gone to the environment, but most of it stays within the bonds, because it needs to maintain that distance, first of all, that brought the two atoms close together. Too close, repulsion; too far away, no reaction. So that optimal distance where, the positive and the negative are also interacting, we need to maintain that. So what is that? That is bond energy that stays inside the molecules, give them the shapes, give them a certain structure. Okay, so, and that maintains the attraction between the nucleus, let me write this down, nucleus of one atom and electrons of another atom. Okay, so that is the main thing. So we see that hydrogen and hydrogen, when they come together, they begin to overlap, and that is called the region of overlap. So this is the region of overlap, in which the two electrons, these two electrons are forming a bond. So the energy needed to make a bond is the same amount of energy that is needed to break the bond. That is the bond dissociation energy, the energy needed to dissociate a bond, right, to make the bond. So remember that if in chlorine, for example, look at chlorine. Chlorine has 17 electrons. So in that 17 electrons, each chlorine has one unpaired electron. So what is happening with that one unpaired electron? That one unpaired electron from each chlorine, when they come, they overlap in that one particular region in the space. So these two oval clouds, when they overlap, these two electrons, they are being shared. Okay, so each chlorine, that's how gets 8 electrons, but at the same time, now it is like also in a bonded state. So it is basically forming a single bond. It's formed a single bond. So single bond is made up of two unpaired electrons. When these two unpaired electrons are paired, then they form a single bond. Okay, so we see that chlorine is basically written as Cl2, two atoms of chlorine. Okay, next is we're going to look at the polar covalent bonds. Now, what are the polar covalent bonds? Covalent bonds are formed by sharing. Okay, these bonds are formed by sharing, but when it's polar means unequal sharing of electrons. So it all depends on the electronegativity, whether these are going to be shared equally or unequally. So it all depends on the electronegativity of the atoms. Now, in your handout on page 8 are the electronegativity values. Okay, and there is also the difference in the electronegativity. So those tables, you're going to consult those tables, and the electronegativity is the electron affinity that has been measured on a scale from 0 to 4. So when the atom has a 4 electron affinity, that means it has the maximum capacity, like it is a highest capability to attract the electrons. And when you go look at this is in the periodic, in your handout, you will see these values. So this is fluorine, the electronegativity is 4. And if you look at cesium, the electronegativity is 0.7. You look at lithium, electronegativity is 1, sodium is 0.9, potassium is 8. So electronegativity decreases when you go down the period, like go down a group, sorry. Look at beryllium, magnesium, calcium, strontium. Beryllium 1.5, magnesium 1.2, calcium 1.0, and strontium 1.0. So the electronegativity differences is getting lowered when you go down the periodic table. Okay, look at fluorine, chlorine, bromine, iodine. Fluorine has a maximum 4.0. Chlorine is 3.0, lesser than fluorine. Bromine is lesser than chlorine and fluorine, that's 2.8, and iodine has the least of all the halogens. So that is the ability to attract the electron. So that is one piece. Next is, as you can see, that a non-polar covalent bond, non-polar covalent bond is formed by sharing, but the electrons are shared equally. That is why the electron cloud is distributed equally. Next is the polar covalent compounds, in which the electrons are shared unequally, as a result of which it forms a delta positive and a delta negative charge. Then comes the ionic compounds, in which the electrons are transferred 100%. So in that case, this is the charge distribution. So basically it's like more in the case of ionic compounds, whereby the electronegativity of the atoms is from between 1.8 to 3.3. That's the difference in the electronegativity. Okay, range. Okay, so look at that periodic table. Look at that, sorry, that's not a periodic table, that's on your handout. And now we're going to look back here. So on a linear Pauling scale, the electronegativity range is from 0 to 4. When this is the difference in electronegativity. The difference, this is called the difference. Difference means subtraction. Difference in electronegativity is subtraction. If that difference is from 0 to 0.4, the atom is non-polar. That is equal sharing of electrons. Equal sharing. And in the case of polar, it is unequal sharing. Okay, so unequal sharing is going to lead a partial ionic charge, partial ionic character. That is where you form the delta positive and the delta negative. If there are ionic compounds, the charges are completely distributed. Okay, complete distribution of charge leads to a full positive and a full negative charge. So it's the ionic compounds. So that's one piece. Now, ionic compounds, when they are in a solid state, they exist with charge distribution. In other words, they exist as the ionic compound, like where metals have a positive and the non-metals have the negative, and they can go their own ways when they break. So that's the ionic compounds. But the same ionic compound, if you heat it and make it into a gas, it's going to convert to, it will acquire a polar covalent character where there is a slight distribution of charge. Okay, not a whole lot, but slight distribution of charge. So anyways, that is the thing. Now we are going to look at the last part, which is the covalent compounds, the bond energy calculations. So the energy needed to make the bond is equal to the energy needed to break the bonds. So here, keep this in mind that the exothermic reactions on one side are going to be endothermic on the other side. Similarly, endothermic on one side is going to be exothermic on the other. Now let's look at the interesting part, which is methane, CH4, made up of 4 CH bonds. Okay, these 4 CH bonds, we know in methane, basically, how do we find out that what is the energy or what is the energy of these 4 CH bonds? So we know of the total when we make methane, when we take 1 carbon and 4 hydrogens, it gives you methane, but it also gives you 1,652 kilojoules of heat. So that's one piece. And if you look at it, it's exothermic on one side. But the same methane, if you want to break it up into carbon and hydrogen, you have to give 1,652 kilojoules of energy to methane. And then in that case, this is acting as the endothermic. Now, here we see that what is the energy of 1 carbon-hydrogen bond. So you're going to take 1652, right? 1652, and you are going to divide that by 4. So 1652 was for the total CH bonds, all 4 of them. So each is going to be 413 kilojoules per mole. So they also get the bond energy values by these mathematical calculations also. Okay. Now there are tables given in the book. Values for the bond energies will be given on the exams, and these bond energies are known, or they find out the bond energies of individual bonds based on what I just now showed you. Besides that, if you have like a molecule in which the bond energies of certain bonds are known, you can find the bond energy of the unknown. So for example, here you have the carbon chlorine bond, right? But we know for the CH3, for 3 CH bonds, we can find out. So in this molecule, what you're going to do is you're going to look at what is it made up of. So this is made up of 1 carbon, made up of 3 hydrogen, 1 chlorine, and that gives you CH3Cl. The total energy it is releasing is 1578 kilojoules per moles. Okay, but in order to find the energy of the carbon and chlorine bond, what are you going to do? We're going to look at the carbon-hydrogen bond that is known, what we did just now on the top, or you can look at the table also. So that is 413 kilojoules per mole. There are 3 CH bonds, so it is times 3, plus carbon chloride, which we need to find, and then 1578 is the total. So next is you subtract the 1578 minus 1239, which is the energy of 3 CH bonds, and you get 339 kilojoules per mole. So this 339 is the energy of carbon and chlorine bond. Okay, so this is how you calculate it. So when we look at it, it is positive. Positive means that this will be endothermic. All right, next is look at another example. And so this is the formula. This is the formula. This is the formula, hydrogen, this one. So bond broken minus the bond formed. And for like a reaction in this case, so if there is a hydrogen and the fluorine reacting and it gives you 2 moles of hydrogen fluoride, then what is the value of delta H here? What is the value of like the total energy of this reaction, the enthalpy of this reaction? So your tables in the book, well, like I said, I didn't see any tables, but some of these tables are actually found in the back of the book. Okay, in the appendix section, they are found. And if they are not, then I will give you, because the book now that I have is this book, the yellow one, this one, and not the big one. But so generally, you know, either these energies will be given and so these values will be given to you. Sorry. These values are given. So hydrogen values are known. And the value of that, the bond energy, the energy present inside this hydrogen bonds is 432 kilojoules per mole. Fluorine is also known, 154 kilojoules per mole. Hydrogen fluoride is also known, 565 kilojoules per mole. But there are 2 moles of hydrogen fluoride, so we have to multiply that. But we are going to use the formula. And what is that formula? That formula is, let me put this in another color. That formula is this, that delta H of a reaction is the sum total of the number of bonds of the reactants times the bond energy of the reactants minus the sum total of the number of moles on the products times the bond energy of the products, the total. Okay, so here we have the bond energies of hydrogen and hydrogen bonds, and hydrogen bonds is just 1 molar, 1 mole times 432 over 1 mole, plus fluorine and fluorine, there's only 1. So 1 FF times the 154 kilojoules per mole. Okay, so these are the 2 product side, the reactant side, which you're going to add. So let's put here, this is the reactant side and this is the product side. Okay, so you subtract it from the 2 moles of 2 times 565 kilojoules per mole. So you cancel out, and eventually when you do the math, you find that the delta H value is 200, and delta H value is negative 544 kilojoules per mole. And so what does this mean? That means that it is an exothermic reaction, and that is the total bond energies. You know, it's always like the bond energies are the energies that are stored inside the bond. So sometimes there's a lot of energy that is stored inside the bond. You give a little bit activation energy and it boom, it gets exploded and it releases a lot of energy it has to the surroundings. Okay, so anyways, this finishes this part, and I am going to, if more examples are needed, we can cover that. But right now, I think this is like sufficient to do these. But if you guys have any questions, you can always ask me. All right, thank you so much, and bye-bye.